Hello everyone and welcome to a video of overfitting. So let's start with the basic definition. What is overfitting? In statistics, overfitting is the production of an analysis that corresponds too closely or exactly to a particular set of data and may therefore fail to fit additional data or predict future observation reliably. It means when we have a set of data, for example, here in this picture, we have some data points and we put an analysis on it, and the learned thing passes exactly through this data, means it learned very well about this data, but when we give the new data, unseen data, it performs very bad. uh, we'll understand in detail how it works. Before that, we learn a basic fact about signal and noise. We will again use the same figure to understand this concept. Let's say this straight line represents the underlying reality, and all these points should lie on this curve as I'm drawing. But the fact is, every time we make some measurement, there is a bit chance due to instrument of measurement, there be a bit variation in each measurement. For example, let's have a simple example. You need to measure a piece of wall with some measuring tape, let's say, and it divide it into meters. First time you measure the wall, it was 15.73, let's say, first reading. Next time to measure the wall, it would be around this figure. Let's say it was 15.77, let's say. And third time you measure the wall, it would be 15.75, let's say. Next time you measure 15.73 again. So when you take a lot of measurements of a same thing with the same instrument, there is a chance of variation on a smaller scale. Same is the case here. When we were recording the actual points, there was a bit noise, as the noise was introduced here. There was a bit noise due to which these points were a bit deviated from the original curve. For example, this point was recorded as this was recorded as this point was recorded as this, and the same is the case. And few of the points were measured exactly on the curve, for example, these 3 points. So there is always a bit noise in the measurements, and each data we have, it is noisy. Keeping this concept in mind, let's move towards our today's topic. The basic thing is learning. How human learn from our real world. When a human see a thing or a event happening for the first time, it is unknown, and it is unknown and don't know about it what is happening. But when the human see the same event or thing repeatedly multiple times, the learning is stored within the mind of a human about that event or thing. Every time when it will see in future a similar event or a similar thing, it would be able to recall that learning and would be able to tell what is happening. But how machine learns? Machine learns from the data. The input data we provide the machine learns from it and store these learning in a way, and it will use that learning in future to predict the things which are similar to the learned model. So let's now understand how this learning is affected by overfitting. Before that, let's look at the basic definition of machine learning. Machine learning is a study of computer algorithms that improve automatically through experience. Uh, Another definition says machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. It means machine learning is a computer science technique in which we build such algorithms which will take the data day by day, time by time, and it will improve its learning on the base of that data. But in this learning process, an effect an effect happened which is called overfitting. So before knowing what is overfitting, let's learn about these three terms, and it will help in understanding us what is overfitting. The three terms associated to machine learning are generalization, overfitting, and underfitting. Our focus is overfitting, obviously, but let's learn these two terms to make the context clear. Generalization is the ability of a machine learning model to learn from data and predict the new unseen data correctly. A model learns from data, its patterns, and its underlying realities, and predicts the new data, unseen data, which it has not seen before, but it give perfect result or good result for that data too. But what is overfitting? Overfitting is when a machine learning model learns specific patterns of the training data, means when the model was given with the data to train itself, it learned the training model so well, but when we give it unseen data, a new data, it performs very bad. And this is our overfitting. Underfitting is that machine learning model was not even able to learn the underlying realities or patterns within the data. So there are two major sub problems under supervised machine learning. Supervised machine learning is a sub problem of machine learning in which our target or our output is already known for the training purposes. So in supervised machine learning, there are two sub problems: regression and classification. Classification is discrete in nature, as its name suggests, that we have an instances of some data and we want to classify it, means we want to assign a class for it. It could be class 1, class 2, class 3, and class n, let's say, and this is discrete in nature. But if for regression, it is continuous. The output could be a set of numbers, a continuous numbers, or a curve which makes a curve, let's say. So let's see the overfitting in these two problems. For regression, the central figure in upper row shows the actual fitting or actual generalization which were actually needed. For example, here in this case, this green curve represents the actual underlying reality, and obviously the blue circles, as we discussed earlier, are bit noisy and lies around the actual underlying reality of the curve. But our red curve representing an equivalent or similar curve, and it would be able, our red curve would be able to predict new points which are similar to this data. And underfitting, for simpler purpose, underfitting is when the actual reality was this green curve, but our model was this straight line and it is not capturing the underlying reality at all. But here is the interesting case of overfitting. Here in this figure, our red curve was so good that it passes exactly through each of the given data set for training, but it does not capture the actual underlying reality, which is a green curve. When we find error or that our model produce for this training data, it will be exactly zero, because it actually passing through each of this point. But when we'll have a new data, let's say we have a new data here or we have a new data here, it will have error and it will produce very bad results. For example, we have here a new point, but the actual underlying curve is very far away from this. For the case of classification, there were two classes, blue circle and red crosses, and for this figure, our model does not classify, does not learn anything. It is just a simple curve and it is not separating these two classes good enough. For the case of generalization, the blue curve is good enough to separate these two classes, but obviously due to noise, there are few outliers which could be ignorable in this case. And here comes the interesting part. For the case of overfitting, the blue curve turned itself so well that it exactly separates these two classes. The blues are at this side and the reds are at this side. But whenever a new instance of this data comes, a new point comes, this blue curve here won't be able to classify it correctly because it is overfitted. So overfitting is very harmful for the machine learning algorithms. The next thing is how we'll get to know that overfitting had happened in our learning process. The simple way is when the learning is complete, we get the error or we get the accuracy on training data and compare it with accuracy of testing data. If there is a huge difference between training data accuracy and testing data accuracy, it means our model has gone biased towards the training data and it is performing very bad on testing data. For example, if a model gives 99.9% accuracy on training data, but it is only giving 50% accuracy for the testing set, it means our model has gone towards overfitting. So this is overfitting, and here are a few ways to avoid the overfitting. We add a validation set too along with the training and testing sets. We increase the data points in training data to avoid the overfitting. We reduces the learnable parameters within the model to avoid overfitting, because as much the number of parameters increases, it increases the power of the model and it could have such power that it even fix the noise. So less parameters, less overfitting. Actually, it should not be less parameters. It should be number of parameters according to the problem. So next solution could be regularization. This is a term which is added in the objective function. So it regularizes the loss or error to reduce the overfitting. And the last one is early stopping. Means we stop our learning process when the learning is expected to be happened, and if we keep on learning more and more, it will go towards overfitting. So we stop the learning process early to avoid the overfitting. Now let's move to Jupyter Notebook and see some Python code where we'll see how overfitting is happened when the mm, power of the model is increased. So here's a bit code. We imported the important libraries which we needed. We created a sample data with a specific function and adding some randomness to the data points, and here is the plot of the data. You can see there is a bit randomness in each data point. We split this data to training and testing data sets. We used numpy function to fit this polynomial on the given data, the name polyfit. So and we also write a function to display the results. Now let's see the example. When we pass a very smaller number, means the model power was only 1, and the model generated only a straight line on the training side. The blue dots are the training data, and the yellow dots are the testing data. So when the power was less, the model was not even able to fit. But if increase the power, models start fitting the training data. But here is the important case. If we go on increasing the power of the model, the curve starts fitting the noise even and forget the underlying pattern actually. And when we reach to the power 9, it tries exactly to fit the noise. And with the increase of the number, when we reach to 12, here is the best example of overfitting. A curve exactly passing through each of the training data point and not covering even a single point of testing data. Here overfitting has happened. Similarly, if we go on increasing the power of the model, the overfitting is still there. We can detect, as we talked about it, we can detect this overfitting with the error. We can see here the yellow dots are representing the root mean square error on testing data, and the blue dots are representing root mean square on training data. We can see from the figure the training error is very low, but at the same time, with the passage of time, as the polynomial degree is increasing, the root mean square error on testing data is keep on increasing, and the gap between these results is increasing more and more. So we need to choose some suitable power of the model where the overfitting does not happen, which should be actually the polynomial power 2, which actually fit the training and as well as the testing data. I hope you enjoyed the video. Please like this video, subscribe our channel, and share this interesting content with your fellows too. Thank you so much. Hope to see you next time.